When we use large language models, we often encounter a common problem: how to adjust certain parameters. The commonly used parameters include the K in top K, the P in top P, and temperature. What impact do these parameters have on large language models? Let's learn about it through this video. Here, we have a large language model. We provided a prompt, "How are you?" which consists of 4 tokens. Next, we expect the large language model to generate a response. The entire generation logic is as follows. When we input a prompt into the large model, it helps us compute a vector representation for each token. This vector representation essentially captures its meaning. The last token is the question mark, for which we obtain its vector representation. Then, through another module, we derive a probability distribution. This probability distribution represents the probabilities of these words being the next token. For example, this is the probability distribution of the first token, this for the second token, this for the third token, and so on. Assume our vocabulary contains 100,000 tokens. Thus, there are 100,000 probabilities. The next token is sampled based on this probability distribution. Naturally, tokens with higher probabilities are more likely to be sampled. However, some words may have very low probabilities. For most words, the probability may be extremely small, possibly nearly zero. But if we use a random sampling method, even low probability events can occur. This is similar to buying a lottery ticket. The chance of winning may be 1 in a million, but that doesn't mean it's impossible. Even under very low probabilities, you might win the lottery. In this context, some words might have very low probabilities. For example, this word might be cat, which has no relation to "how are you?" However, there is still a chance of sampling it randomly. So, is there a way to exclude tokens that are unlikely to follow "how are you"? This process can be controlled through the top K and top P parameters. Top K means only considering the top K tokens with the highest probabilities. For example, if equals 3, though in practice, K is usually larger, we only consider the top 3 tokens with the highest probabilities. From the graph, these might be I, am, and fine. With top K, the next token is sampled from this limited set of 3 tokens. All other tokens are ignored. For example, if the probabilities for these 3 tokens are I 0.1, fine 0.07, am 0.03, the next token is sampled based on these probabilities. However, we must ensure the total probability equals 1. Currently, the total is 0.2. To adjust, we normalize the probabilities. Multiply each by 5 to make the sum equal to 1. I 0.1 times 5 is equal to 0.5, and so on. Now the probabilities sum to 1. The next token is sampled accordingly. For instance, I is most likely to be selected, but fine or am might also be chosen depending on the sampling. Essentially, top K pre-filters tokens that are unlikely to appear, reducing randomness and improving control over the model's outputs. Top P works on a similar principle, but with a different logic. Here, we specify a cumulative probability threshold, P. For example, if is 0.7, we include tokens until their cumulative probability reaches or exceeds 0.7. Here's how it works. Sort tokens by probability, with the highest probability token first. For instance, I might have 0.1, fine might have 0.07, and so on. Start accumulating probabilities. I 0.1. Cumulative probability equals 0.1. Fine 0.07. Cumulative equals 0.17. Am 0.03. Cumulative equals 0.2. Continue adding tokens until the cumulative sum equals or exceeds 0.7. Once this threshold is reached, the selected tokens form the candidate pool. The next token is sampled from this pool. Tokens outside this pool are ignored. Both top K and top P aim to reduce the large vocabulary, for example, 100,000 tokens, to a smaller candidate pool for the next token. However, their logic differs. Top K fixes the number of tokens K. Top P uses a probability threshold to dynamically adjust the number of tokens. For instance, with P equals 0.8, the candidate pool might contain 100, 200, or even 600 tokens, depending on the probabilities. By designing parameters like top K and top P, we can better control the model's outputs, reduce randomness, and achieve more consistent results.